Welcome back to Finite Element Methods, class number 20. This is November 6th, 2025. We've been discussing parabolic problems, and we discussed in pretty good detail what we mean by a weak solution. We discussed properties of weak solutions. We discussed the Galerkin approximation of the solutions to parabolic problems. And we used the diffusion equation or diffusion problem as kind of our prototypical, a linear diffusion problem as kind of our prototypical parabolic equation. We discussed semi-discrete and fully discrete Galerkin approximations. The fully discrete, the only one that we've demonstrated so far is what is called the backward Euler or implicit Euler Galerkin method. And so if we have time, we're going to fully analyze both the semi-discrete approximation and the fully discrete backward Euler Galerkin approximation in this lecture. To do that, we need a tool called the Ritz projection. So what's the Ritz projection? Let omega be an open polygonal domain in R2. We don't have to stick to R2. We can be or operate in RD. So this is not a huge restriction for us. Suppose that U in H01 is a given function. The elliptic or Ritz projection of U, which is denoted like this or with this symbol, RHU, is a function in VH. In this case, we're going to take VH to be the standard finite element piecewise polynomial space, M0R. The zero indicates that we're enforcing zero boundary conditions for the functions. This object is defined in the following way. This is our standard bilinear form, our energy bilinear form, and we demand that RHU against test function psi is equal to U test function psi for all psi in VH. This is how we define this object called RHU. Well, what is this actually? If I look at it, if I imagine this U solves some sort of standard elliptic problem, then we would be solving, well, if it satisfied that standard elliptic problem, then U would satisfy this equation for any psi in H01 or the subspace. But now we're not identifying U to any F. And this would be the weak formulation of this problem, right? So we're not really identifying U with any specific F. We're simply saying we have this U. It could solve a elliptic problem in the usual sense, but it doesn't have to. If it did solve that problem, then this would be equal to that. These two things, this object would be equal. And basically we would be asking, what is this object here for any psi in the finite element subspace, which equals this? Well, that's just the finite element solution. So really all this is the finite element version of U. The finite element version of U. So what it does is it takes U. What it does is R takes U, which is in H01, and it's going to push it into the finite element space. And the way it does this is through this equality. So what we're saying then is if you can think about it this way, if U solves that elliptic problem that I just erased, then Laplace minus Laplacian of U is equal to F. This is just the standard finite element approximation of the solution U. It's just the finite element version of U. We call that the Ritz projection, even when U is not associated to some function f. Okay. So if you don't like that, if you don't like that description, then I can pose it to you this way. Well, this problem I can show is uniquely solvable. I can always find a solution to this problem. And it just so happens that it looks like a finite element solution. Just look at this part here. That looks like a finite element solution where normally on this side it would be some given data. I can show that this RHU exists, and I can show a few more properties about it as well. Well, we call it a projection because it actually is a projection. RH, which takes my smooth functions or my infinite dimensional functions and pushes them into the finite element space, is a linear projection operator. That means if I apply it to itself, I get well, that's not really fair, I should say. A projection operator means that if I apply it to itself, I just get itself back. In other words, RH squared is just equal to RH. That's what a projection operator is. It's linear because I am defining it through a linear process, and it satisfies a stability condition, namely that RHU in the H1 seminorm is less than U in the H1 seminorm. The nice thing about this is that no matter how small H gets, this guy is not going to blow up. It cannot blow up because it's bounded above by this number for every given U. Okay, so that's a concern for some numerical approximations. If H is made smaller and smaller, the approximation that I'm generating could blow up because it's not stable. In this case, we have stability, and it's this type of stability here, which prevents us from blowing up. So we call this stability. Now, furthermore, if elliptic regularity holds for the problem, you remember what elliptic regularity means. It means if f is an L2 function, then actually u is an H2 function, and I have some other nice features as well. If that's true, and we have this additional smoothness, then we have this estimate. The difference between u and RHU, is less than this amount. Now, what is this? Where does this come from? In fact, all this is if I drop this part, okay, well, let's just drop this part actually, and divide both sides by h. So this is going to say that this is h, or no h over here, hs minus 1 over here. Actually, let's take s to be this largest possible value. It can be as large as r plus 1. So this would be hr plus 1. I would lose a power of h. So let me write out what that says. That would say, and I'm going to try to convince you that this is something you've seen before. In fact, many, many times before, because we've repeated it many, many times. If I just look at that, this is r, u, h, r plus 1. So what is this? Well, this is just the standard error estimate for the finite element scheme. Here's the finite element, or here's the true solution. This guy is the finite element approximation. This is the energy norm. It's less than c times h to the r power, where I'm using piecewise polynomials of degree r. Okay, did I mention that somewhere? Should have said that here. I'll make a correction later on. This here is piecewise polynomials of degree r. I think I failed to say that elsewhere. Yeah. So I'll fix that up and I'll repost that. This is just the standard error estimate for an elliptic problem. It could be non-symmetric or symmetric, either way. But now what happened whenever we did that Nietzsche's trick? Nietzsche's trick said that you gain back a power when you go to the L2 norm, when you investigate the size of the error in the L2 norm. That means if we were to investigate the size of the error in the L2 norm, we would gain a power back. So this would be R plus 1 if we did that. So if I combine those two ideas together, then I get this estimate here. But it just so happens that it's true for any S up to and including R plus 1. If you don't like that, you can just think about S being its maximum value, which is R plus 1, and then it comes out to be what I just said. So this problem here, or this part of the result that I'm claiming here, doesn't need to be proved because that's what we've already shown. We've already done this. The only thing that it requires is that you kind of stand on your head and realize that this is something we've seen before. This is just the finite element approximation of U. If U satisfied a certain PDE, right? Laplacian minus Laplacian U equals F. But actually, it doesn't have to satisfy any particular PDE. It doesn't have to be associated with that. We can simply approximate U with its finite element approximation directly. And the way we do it is through this definition here. Okay, so I claim this part we don't need to do because we've already done it. But this part here, I'll show you how to do that. The fact that it's linear is just due to its definition. We're using linear process to define this thing called the projection operator, and that conveys linearity to this operator. The fact that it's a projection is also straightforward. I'll let you think about that one. So let's only tackle the stability question. To see stability is true, let's go back to the formulation. And here we're allowed to plug in any function from VH. So the function that I'm going to use is this guy in particular, RH of U, because that is a finite element function. That whole thing is a finite element function because this operator pushes this infinite dimensional thing into the finite dimensional space, VHR. So I can put that object in for the test function. And when I do that, putting it in this location, I just realized that this is nothing more than the energy norm squared, right? That's the H1 semi-norm of RHU squared. Now, on the right-hand side, with my definition, I have this. And the way I can take care of that is just apply Cauchy-Schwarz. Cauchy-Schwarz says right away that this is less than U in the H1 semi-norm times H1 semi-norm of RHU. And now I have square over here and a single over here. By cancellation, I can reduce that, divide both sides by that. Now, the only way I can't divide both sides by that is if RHU is equal to 0, but I'm going to assume it's not equal to 0. Or I guess it could be a constant as well. I'm going to assume that this norm is not equal to 0 so that I can use cancellation. And if I do, I get this, which is precisely equal to the projection, or not the projection, but the stability that I claimed. We're right here. That's the stability I claim. So this Ritz projection operator is quite useful to us, even though it seems like it's really nothing. It turns out this is going to be a key to the analysis that we do. We're going to use this again and again. So the first time that you see me use it, you'll probably be puzzled. The second time and the third time, I hope you'll get the drift and get the idea of what's happening. What it does is anytime we have an object like this, where the test function is from the finite element space, I can replace this object, which I'm going to see plenty of, with this object, which has some certain nice properties because they're exactly equivalent on the subspace. All right, now what we want to do is focus on that semi-discrete Galerkin approximation for the diffusion problem, that model parabolic problem that we want to solve. So how does this work? Well, first of all, let's assume that the hypotheses of theorem 20.2 are satisfied. That means for the domain that we're working on, we assume the regularity condition holds. That's going to allow us to assume everything that we just proved here. Okay, so this is going to be true, and that's going to be true. Okay, so that's the hypotheses of theorem 20.2 unlocks that for us. Suppose that U is the solution to this. This is the parabolic problem. You might remember that before I said, well, we have to make this duality pairing because this object here isn't necessarily an L2 function. In general, it's a function L. But now we're going to apply enough regularity to say that that is actually going to be a regular L2 function. And so we can just use the regular L2 inner product there. Suppose that U is a weak solution in this sense, and U satisfies the initial conditions. We're going to assume that we have the following regularities for U. U is going to be assumed to be in L2 0T H01 intersect HR plus 1 intersected with, so this means U is in this space and it's in this space, intersected with H1 0T HR. So let me remind you what these regularities mean. So this means that at each time I have this much smoothness for my function U. This says that U and its first derivative are both nice functions, okay? And in particular, its first derivative is actually for each time going to be an HR plus 1 function. Furthermore, these two regularities say the following two integrals, which are essentially the norms, are going to be finite. 0 to t integration, the norm HR plus 1 of U squared dt is less than infinity. So that says that this norm, actually this is a norm squared, is less than infinity. So we get L2 is what gives us this power, and this norm is shown here. What does this guy say? This says something both for the function and for its time derivative, but I'm only going to focus on the one for the time derivative. This says that the time derivative has this norm, actually it's a norm squared, being finite. Integral 0 to t HR plus 1 norm of the first derivative with respect to time. So this out here tells you how many time derivatives you can expect to have this much regularity. Okay, if it says L2, then it's 0 derivatives in time. If it says H1, then it's 1 derivative. If it says H2, then it's 2 derivatives. This says H1, so that means 1 derivative has this integral norm squared being finite. This HR plus 1 corresponds to this norm. This is essentially an L2 space, so that's why we square this guy. All right. Now, we're also going to assume that the initial conditions has, right, this is the initial value here, has some nice spatial regularity. Normally, we would just assume this. In fact, we don't even have to assume that, but we're going to assume that it has this regularity H01. Sometimes we can assume it's just an L2 intersected with HR plus 1. So this is the Sobolev space, HR plus 1. So this means weak derivatives exist in our L2 functions of order up to and including the R plus first. And we know what the norms look like for those spaces because we spent a lot of time talking about them. Okay, so that's That's the preliminary stuff. That's what the solution U is going to satisfy. It satisfies the PDE plus it has additional regularities as mentioned here. Now, on to the finite element solution. Suppose that the semi-discrete Galerkin approximation satisfies this equation. That's just the definition of the semi-discrete Galerkin approximation. We're going to assume that UH at time 0 is equal to something called VH. Now, VH, the only way that this can make sense is if this object over here is actually in the finite element space. And the way we're going to get V into the finite element space is by pushing it into the finite element space with another projection operator. So the projection operator that we want to use is, we're not going to specify what it is at the moment. Later on, I can show you what you might choose. We could use an L2 projection operator. We can use the one we just defined above called the Ritz-Galerkin or the finite element projection operator. But for right now, all we need to know is that this guy pushes an infinite dimensional function into the finite dimensional space VH. In this case, VH is just equal to their standard finite element space, piecewise polynomials of degree at most R. Here's the punchline of the theorem and what we're going to work today to prove. The difference between U and the finite element approximation, this is called the error, in the L2 norm is less than the L2 norm difference of V and VH. What is this? This is the error between V and its finite element projection into the space, measured in the L2 norm, plus C times HR plus 1 power of, so this whole thing multiplies this sum in parentheses here, the HR plus 1 norm of V plus the integral 0 to t, this should be norm squared, I believe. So there's a typo fixed. Okay, integral 0 to t, HR plus 1 norm squared of d udt ds. So remember, we said that this integral should be positive from above. How do we know that? Well, that's part of this integral here, except we're not integrating all the way up to capital T. We're going to stop at some arbitrary t, okay, in the interval 0 to capital T. Notice I've changed my my variable of integration here, which is still integrating in time, but I'm just going to switch that to s. So you see that my assumed regularity means that this integral has to be bounded, okay? And I could, if I want to come up with a larger upper bound for this right-hand side, I could run this small t all the way up to capital T. I have that much freedom and flexibility to do that. But in this present form, this estimate 20.4 has a lot of detail in it. And so this is what we want to show. It turns out showing this is very tedious. Okay, it's going to take us probably the rest of the lecture to do this. And so we want to take our time and understand every aspect of this. Okay, so let's get started. So here's the proof. We want to start out by setting this variable e to be u minus uh. So this is the true error. This is the PDE solution minus its Galerkin approximation. Notice that this is a function for every time, it's a function in H1. This is a function also in H1. The reason why it's in H1 is because it's in the subspace VH for every time step. So it's fair to take these two functions and subtract them. They're in the same space, so I can subtract them. However, notice that this difference function isn't in VH. Why? Well, this VH is a subspace of H01, but this function here is not in VH. So if I take the difference of these two functions, this guy is probably not going to be in that space, so the difference is not going to be in the space. However, it's going to be useful later for us to have some part of the error in the space VH. And here's how we're going to do that. We're going to redefine this object called the error by adding and subtracting a term. Okay, so we're going to add this term and then subtract it right back. So we see that this is exactly equality. I'm going to add and subtract, as I said, RHUH. Actually, that doesn't make sense. That's a typo. Let's fix that now. There should be no H there. Okay, it's just RHU. There we go. All right, so what is this? This is the Ritz projection of the continuous function u into the finite element space. So this new difference that we get on this side is what we're going to call rho. This difference over here, RHU minus UH, what is that? Well, I don't know what it is exactly, but whatever it is, it has to be in VH because it's the difference of two VH functions. Okay, so now this difference, let's think about that. What is this rho? Well, this is just the difference between a function u and its Ritz-Galerkin approximation. We have estimates for the size of that error already based on our assumption, our hypothesis from theorem 20.2, the result of 20.2 really. In any case, we've just split the error into two new functions, rho t and theta t. But the important point is that theta t for every t is going to be in the space VH. This is a very important point for us, one that we're going to exploit later. Now, by theorem 20.2, because this is just the difference between a function and its Ritz projection at every time step t, I know that measured in this norm, this kind of weird norm with this h over here, is less than CHR plus 1 times the HR plus 1 norm of UT. I'm taking this all the way up. So in theorem 20.2, I could take this from S equals 1 all the way up to R plus 1. I'm taking it all the way up to R plus 1. Okay, so that's all we need right now for that rho. We're going to put that away and put it in our pocket for a while, I think. Well, actually, we're going to transform it a little bit. So um, don't put it in your pocket too deeply because we are going to transform it. I forgot about that. Okay, so let's have a look at this guy and see if we can transform that a little bit. All right, so what we're going to do is we're going to realize that because U has sufficient regularity to do this, that the fundamental theorem of calculus holds in this sense. If I integrate from 0 to t, the weak derivative of u du dt s ds integrated from 0 to t. So this is just fundamental theorem of calculus. Does it apply for functions of the regularity we've assumed? The answer is yes. And I get the same result that I would normally get from the fundamental theorem of calculus. This is going to work out to be u of t, so it's just the function at t minus the function at 0. But what is the function of 0? The function of 0 is just v. Okay, so that means what I can do is I can take this object here, and I can replace it by using the triangle inequality with this object here. I'm going to take this and I'm going to put it in there. And then I'm going to apply the triangle inequality to what's left. Of course, this is just going to be u of t is just going to be v, and then this integral. And I claim that what you get when you put it in there, you can discard this guy. We don't need that. You can discard that. How do we discard it? We simply say, well, this is just bigger than the norm of rho. So I'm just going to get rid of that guy, right? And all I'm doing here is putting this function in that norm there, and I claim what I get out on the other end is this. The C and the HR plus 1 simply come down. And so it's up to you to show that when I do this replacement in here, then I just get this, all that. You just use a triangle inequality and you use a realization that this spatial norm can be, if I estimate this guy as a spatial norm, then the spatial norm can come inside. So I'm going to leave that to you to show, just a little exercise. Or you can just take it on face value if you want. Now, what do I have? Remember, the thing that I ultimately want is this error in the L2 norm. But by the triangle inequality, this is equal to rho plus theta. So I can show that this error is less than this norm plus this norm. I just showed that I have an estimate for this guy up here. So I'm going to put that estimate there, but I still need to estimate this guy. So the rest of the proof is going to be focused on that. And essentially, I want to show that what is left is more or less exactly the same here in terms of its size and error. So what is left is not going to be bigger than this. In fact, I can hide this in that. Okay, I can estimate this term by something which looks like this term. And so I'll be able to say, I'll be able to conclude my theorem from there. So as I said, to complete our proof, we must bound this guy in the L2 norm. This is a spatial L2 norm. And so what we're going to do that is form an error equation for theta of t. Here's how we're going to form that error equation. All right, we're going to start with 20.2. That is the weak formulation of the PDE problem. So there's 20.2. Except that, well, for now it's fine, but just notice that the test function can be anything in H01. But I'm going to apply this to test functions in VH. And the question is, will it still hold for test functions in VH? The answer is yes. It'll still hold for test functions in VH because VH is a subspace of H01. So I can use that fact to replace this test function with a test function, which is arbitrary, from that space. When I do that, then I can use my definition of the Ritz projection and replace this object with, remember, this is just the A bilinear form of U and psi. Once I restrict this to the subspace, then I can replace this object here with exactly that. So that's what I've done. I've simply replaced this object with this once I replace this test function with a test function in VH. In other words, I've used the fact that this holds true for everything in H01 and the fact that VH is a subspace of H01 to get to here. Now, I've also done something else. Here, I have the time derivative. I'm going to add and subtract the same term. So I've changed nothing by going to this equation here. It's still the same as above, and it's still satisfied with equality, but notice that the test functions are coming from the finite dimensional space. Okay, now, what is this object? What is this object here? What's this object right there? And let's make sure that we get the sign correct on everything. Well, this object here is just going to be the time derivative, right? I can hopefully use the linearity of the weak time derivative, and I can pull out, well, In fact, it's a little bit like using the distributive property, but it's actually just using the linearity property. What's left, or what's going to be left there, is going to be u minus r hu. What is that? That's just rho. Okay, so I'm going to take this term owing to this part of that, and I'm going to throw it to the right-hand side. When I do that, it lands right there. That's exactly what that term is. Okay, so that part I've thrown over, but what's remaining? That part. Notice that my test functions have to remain because I'm using the Ritz projection as a replacement for u. I'm using the Ritz projection. I have to use test functions from VH. Okay, now all that we have to do is we're going to take this 20.6 and we're going to subtract it from the Galerkin approximation. What does the Galerkin approximation look like? We'll go back to 20.3 and have a look at that. When I do that subtraction, then I'm going to get the following. This is starting to look like an equation for this part of the error function, theta. Okay, why does f go away? Why does f psi go away? It's because that term appears both in 20.6 and 20.3 exactly in the same form. And when I do the subtraction, that term goes away. Why does this term change sign? Well, it's because I'm subtracting 20.6 from 20.3. So I do a minus of a minus and I get a plus of that term. What we've essentially done is formed an equation for this part of the error called theta, and the forcing term for that theta is this weird part of the error, the time derivative of rho. But the nice thing is this equation, this error equation, holds for all test function psi in VH. So phi is in VH, psi is in VH, we can set psi equal to theta. And that's what we do. When I do that, I get for the first term that this term is just the H1 seminorm squared of theta. And of course, this term is as shown here. Now, for this term, we've seen this type of calculation many times, but normally we stopped here, but we're going to carry this a little bit further. I showed you before why this is true, but if I look at that and just think about this as just being a function, clearly this is true as well. So what I'm going to do is I'm going to use this replacement. This term is equal to that one. I'm going to sub that in here. If I do that, and I'm going to drop this term because I don't need that. What do I mean by dropping terms? So I'm going to estimate from above, and so to drop that term means I'm just going to throw this positive term away. The reason why I can throw it away is because it's obviously positive, where it's non-negative. So I can say that this is greater than or equal to just this term. So I keep that, but replace it with this. On the upper limit side, it's less than this. Okay. No, let's see. Yes, I just did it in 2 steps. So I have here, but this is greater than that because that is just equal to this. On the upper side, it's less than that, or it's actually equal to that, but we're going to use Cauchy-Schwarz on that term to break it up into the product of these 2 error terms. And then once I get to this spot, I can cancel, right? Using cancellation property again. And we're going to assume that, and the only way I couldn't cancel is if these error terms were 0. Well, they're only 0 if theta is exactly equal to 0, so we're going to assume that that's not true. And the thing that pops out in the end is just this. So now we're getting close. We're going to integrate this term, and we're going to integrate from 0 up to any final time little t. Now this term is an exact derivative, right? So when I integrate that, what happens? Well, you just use fundamental theorem of calculus once again. And I get theta of t, well, norm of that, evaluated at t, minus theta at 0. But what I'm going to do is that minus theta of 0 term, I'm going to throw over to the right-hand side. And it's going to accompany this guy. But of course, now I've integrated that term, so it looks like this. My variable of integration, I don't want it to be t because I'm using t as an upper limit, an arbitrary upper limit. So I'm going to set that integration variable to be equal to s. So I hope you see why this is true. Let's estimate this guy, this term right here. This term, well, what is that? Theta of 0, if I look at it, it's just going to be RHV minus RHV of V minus VH. That's how theta of 0 works out to be defined. Normally, it's just RH of U minus U, okay? Or sorry, RH of U minus UH. But UH is equal to VH at time 0, and U is equal to V at time 0. Now I'm going to add and subtract V. So this is changing the expression not at all. But now I'm going to regroup this term, and I'm going to use triangle inequality. RHV minus V. Well, this I already know an estimate because I know that if this is smooth enough, then the difference between a finite element function and the original function itself, the Ritz projection and the original function, is something that I can estimate. Well, actually, that's the one I need. What about this guy? This guy here, I'm just gonna leave it back in its original form. Remember, VH is equal to PHV. I'm just going to convert it back to VH because I don't need to change it. This is going to end up in the final form of my error estimate, and so I'll keep that. What about this term? Now I have to make an assumption about this term. Let's look at it. This term is going to be the time derivative of rho, but what was rho? Rho is U minus RH of U. So we're going to make it the reasonable assumption that this guy, if it's smooth, it's still going to be, or it's smooth enough, it's going to have a weak time derivative. That's one assumption that we're going to make. In fact, this can be shown with the assumed regularities that we've have above. We're also going to assume that I can interchange these two operators. This is an operator called the weak time derivative, and this operator here is the Ritz projection. I'm going to assume that I can interchange Ritz projection with the time derivative. Okay, that seems reasonable. And in fact, if you go to this reference Tomei, which I put in the references section on our Canvas site, this is where I'm drawing this material from. You can show that the regularities that we've assumed allow us to do this interchange. Okay, so now I'm going to do that interchange in this term and this term here. Okay, so that's going to be, now I can show then that this term is equal to this. And all I've done, the only difference is from here, I've just interchanged those two operators. I've put the weak time derivative right on U. And so now you see this and this, those are the same. So this is just the difference between a function, I don't care what it is, and its Ritz projection. Well, I know how to estimate that because by the assumptions that I have available to me, the regularities that I have, this is just the difference between a function and its finite element approximation. So going back to theorem 20.2, I'm allowed to assume this for the L2 norm. For the L2 norm, remember the L2 norm gains all of the powers of H that are available. There's R plus 1 is available. So now I'm going to combine all of the estimates that I have so far, 28, 20.9, and 20.10, and that's going to allow me to estimate this guy. This was our 20.8 from above. I'm just replacing the values of these two norms that I now have estimates for. And I get an estimate for theta of t in the L2 norm. Okay, so 20.8 told me something about the size of this guy, and I replace it by 20.9 and 20.10, allowing me to conclude this estimate here. Notice that I haven't gotten rid of this. I haven't tried to estimate the size of the difference between V and VH. I'm going to let that alone. I'm just going to say you can make that decision later, exactly what projection you want to use. And then once you know the projection, you can use that and use the error estimate for that. For example, I could use the interpolant. The interpolant, I know the error estimates for that down to the final form. Okay, so now if I recall 20.6, 20.6 said that I had this term. This was almost the very first estimate that I formed. And then this guy, which I said we had to work hard to get. Well, now I've worked hard and I've gotten an estimate for that. And I'm just going to apply it right to there. Well, when I do that combination, you'll notice that some terms that are already here appear again, like this guy and this guy. I can just combine those with the terms that are already present and make a new constant. And so that's what I did. I made a new constant. What terms don't fit anywhere with what's already seen? Well, this guy. This guy doesn't fit anywhere that we already have. So what we're going to do is just let him alone. Just let him be by himself. And this is the desired error estimate that we wanted to prove. So U minus its semi-discrete Galerkin approximation for this diffusion problem measured in the L2 norm is less than a constant times h to the r plus 1 power times these norms plus this guy. What can I do about that? Well, if I use the interpolant or the Ritz projection operator, both of those I know are going to be less than a constant times h to the r plus 1 times this. So I can, if I use either the interpolant or Ritz projection because they're optimal order projections, I can hide this term in here. And so I could just gain an error, which is just this. So what is this saying? This is saying that if I use my semi-discrete Galerkin approximation, then it's order r plus 1 in h if I measure the error in the L2 norm. So that's what we call optimal order. It's an optimal order error estimate. It's order r plus 1 in h when measured in the L2 norm. Okay, so that is how we estimate this semi-discrete Galerkin approximation of the diffusion problem. So with that, I'm going to pause there and I will take your questions. You can turn your cameras back on. All right. So I apologize for that internet glitch. I wonder if the internet's come back on. Don't know. I eventually I had to unplug my internet from my laptop and turn off and turn the Wi-Fi on because I use an Ethernet line and use my my hotspot from T-Mobile. So far so good, but I'm not sure. Never experienced an actual internet outage here at UT, and I guess you guys aren't on campus, so that's good because you're not having to experience it. All right, so any questions about that? I know it's a little bit of a, this is a weird, these are weird error estimates and probably like nothing you've seen before. I guess what I have to say about this one is it's not so important. It's not so vital because actually this approximation process, the semi-discrete approximation process called the semi-discrete Galerkin approximation, isn't fully practical because you still have to solve an ODE problem in the end. And so we want what's called a fully discrete version of this. And so that's what we're going to start to analyze next. I won't be able to get very far into that analysis. So what we'll do is I'll start it and then we'll pick up again with it next time. Okay. Any questions about what we just did? I
I was
know
about to
it's
ask the question, and you said exactly what my question was. Is it practical? So
yeah, it's it's I think the best way to view it is it's getting us used to the tools that we're going to use for the fully discrete case. Okay. Any other questions? Okay, you can turn your cameras off and I'll start that next proof. We won't get through all of it. All right, so we just concluded the proof for the error estimate for the semi-discrete approximation, the semi-discrete Galerkin method applied to the diffusion problem. We showed that we got optimal order error estimates in that case. And so now we realize that that estimate is useful and interesting, but it's not for a method that's fully practical because it's only semi-discrete. The only way that we can get a fully practical method is if we go to the fully discrete setting. Now, we had a method already that we mentioned that we've defined already, and that is the implicit Euler or backward Euler Galerkin method applied to the diffusion problem. That's what we want to analyze with this theorem. You'll see a lot of the same themes coming back in this proof. We won't be able to get through all of this proof this time, but we'll just get through the statement of it and maybe a couple lines, and then we'll come back to it in our next lecture. So here's the statement of it. Suppose that the hypothesis of 20.2 are satisfied. So that's that regularity assumption so that we can assume that and so that we know that the Ritz projection has certain nice approximation properties. Assume that U satisfies this weak formulation of the diffusion problem. Again, I don't need to use the dual pairing here because I'm going to boost the regularity of that so that it's a regular function. Of course, it satisfies the usual initial conditions, but we're going to boost the regularities by assuming that U satisfies these two regularities. These are the same that we had previously. I'm going to add to that another regularity. This one's new, which says that U is also in this space H2 0T L2. What does this mean? The H2 means the number of derivatives that I could expect for U. I'm going to look at only the highest derivative. So that's the second derivative with respect to t of u. This is time derivatives. And that one should be measured in the L2 norm. And this square comes because H2 is really an L2 based norm. So it's going to be L2 in time of the second time derivative. So this norm, it's actually a norm squared, has to be finite according to that hypothesis there. So I've explained these two already. This is the new one. We're going to assume that UHK satisfies the backward Euler Galerkin scheme. So this is recall the definition of my backward Euler Galerkin scheme. This object here is not a time derivative, it's a time difference. Okay, UHK minus UHK minus 1 divided by S. Now S is equal to our, I should probably make that a defined quantity. This is our time step, and it's defined as T over capital K. So notice that I differentiate little k's from capital K because I really emphasize this arm here. Okay, I exaggerated a bit. So this guy, I hope you can see, is definitely not a lowercase k, it's capital K. It's a little bit hard to make capital K when in handwriting, but that's what it is, capital K. Now, capital K is, that's the total number of time steps that I want to take. So I'm looking for this function UH little k from little k equals 0 up to capital K, satisfying this equation. Of course, if it's the Galerkin method, then the test function is, of course, taken from the finite element space. And the finite element space here is the usual standard piecewise polynomials of degree r. Then I'm also going to assume that v minus vh in the L2 norm is less than this estimate here, a constant times hr plus 1, hr plus 1 norm of v. This is just an optimal order error estimate. If I were to use the interpolant or the Ritz-Galerkin projection, or the Ritz projection operator, uh, to calculate this guy, then this optimal order error estimate will hold. So basically this is saying if you use interpolant or the Ritz projection, either way. So remember VH we said is equal to PHV. And all I'm saying is you can either take this to be the interpolant, which we called pi h, or the Ritz projection operator, which we called RH. And this type of estimate is going to hold in either case. Okay, if that happens, then this is how we're going to measure our error. UHK, remember in my backward Euler-Galerkin method, I have to compute these approximations not for every time, but for these punctuated times, these time, I guess, time intervals. K equals 0, K equals 1, K equals up to capital K. I'm only getting a discrete number of those time values. So I can only measure the error in the L2 norm at those punctuated um, time slots, TK. So, by the way, what does TK mean? Did I define that object here yet? No. So I should have. Thought I did already, but I guess I did not. Okay, so what does TK mean? So I'll make this clear with when I make some corrections to these notes. TK is just S times little k. So I can only measure the difference at these discrete times, not all times. Now I get pretty much the same term that I got previously for the spatial part. And I think I have a missing a parentheses there, so let's correct that. There we go. So this is the same that we got for our previous analysis. The new term is this guy right here. So remember this guy, I think I want to use a different notation for that. Just I want to be consistent. So we're going to use TT. So what is subscript TT? That means second time derivative. We said that that guy, this object here, is finite because of this regularity assumption. So this here can be treated as a constant. So what is this saying? This is saying that the error measured in L2 norm is less than a constant times h to the r plus 1 power. This is all just a constant term. Okay, it just depends on the true solution. So we can treat it as a constant. It's independent of h and independent of s. And this term we can treat as a constant. I could, if I want to, run this guy up to capital T and replace this with something bigger. That makes it a true constant. Same with this. So this is saying that our fully discrete method is order r plus 1 in space and order 1 in time. And that's what we expect. That's exactly what we expect. So we say again that the Euler method is an optimal order method. It doesn't have the highest possible order that we can find. We can find methods which have better orders of accuracy. For example, we can find methods like the Crank-Nicolson method, for example, where this is s squared. We can do a little bit better there. But in this case, it's optimal for what we would expect it to be given how we've defined it. So how do we prove this? Well, I'm going to run down through this really quickly, but we're going to pick up here and redo this next time. So as before, what we're going to do is break our error into two parts, a rho of t, which is going to be ut minus rh ut, and a part which is always going to be in the finite element space called theta. Now, theta k, I'm only going to define at the discrete time instances, tk. So it's going to be RH u of tk minus RHK. That's the fully discrete finite element solution. Then I can show that my error at these discrete time periods, tk, is equal to rho of tk plus theta k, which I can define. I can just define this object as rho k. This is not a power, by the way. This is a superscript indicating time, which is defined this way. So again, this are only defined like my approximation at these discrete times tk, whereas rho is defined at all times, but I can always restrict that to the discrete times that I'm interested in. As before, in the previous proof, we have a straightforward quick estimate for rho. We don't have to do anything about that. But what about theta? Theta, we're going to have to, again, devise an equation for theta and then analyze that equation for theta separately. So how do I make an equation for theta? Well, I'm going to use some tricks like I used last time. My I start with my PDE, or I start with kind of the infinite dimensional version, and I restrict the test functions. Instead of on H01, I restrict them to be from the finite element space VH. Once I do that, then I can replace this term, which was here, um, nabla u nabla psi, with this updated term, and that's due to the definition of the Ritz projection operator. Once I do that, then I can change this term around a little bit, and I can get to this. So this is almost the equation that we want. What we do is we go back to the backward Euler-Galerkin scheme, and we subtract, and then finally we get an equation like this, which is an equation in theta. Once I'm here, then I can realize I can replace this psi with theta k because it's in the finite element space, and this allows me to get an equation that is entirely in theta. The forcing function over here, I haven't broken this down yet, what this wk is. It's defined up here. This is a little bit like the forcing term that we had before. So to get to move the error estimates beyond this part, I have to do some new tricks that you haven't seen before, and these are we will review in detail next time. And we'll start here and proceed through this proof when we meet again, which I guess will be Tuesday. So with that, I'll end this lecture and take your questions.